In this video, we're going to talk about the Nernst equation. So the Nernst equation is a way that we can calculate and convert between standard cell potentials and cell potentials under other conditions, under non-standard conditions. So if we think back to thermochemistry, we learned that delta G was equal to delta G naught, which is delta G under standard conditions, plus RT times the natural log of Q. We also talked about earlier in this chapter that delta G in electrochemistry is equal to the number of moles of electrons times the Faraday constant times the cell potential. Well, since both of these are delta G, we know that delta G is equal to delta G naught plus the RT ln of Q, and it's also equal to negative NFE. So we can set these two equal to each other. And I'm not going to go through all the derivation here because it's really kind of beside the point. I'm not going to ask you to derive the equation. But if you put these two together and do some mathematical rearrangement here, we come up with the fact that the cell potential is equal to the cell potential under standard conditions minus RT over NF times the natural log of Q. Or we can rearrange this to have log base 10 rather than the natural log. So in order to do that, we can multiply RT times a factor 2.303. Now we know what the value for R is. That is 8.314 joules over the joules over Kelvin times moles. And if this happens to be at 25 degrees Celsius or 298 Kelvin, we can multiply 2.303 times 8.314 times 298 and convert this, use conversion factors to convert this into volts. And we come up with the cell potential is equal to the standard cell potential minus 0.0592 volts over N times the log of Q. So again, I'm not going to take this derivation step by step because the derivation is really not necessary here. What we're really interested in is this final equation. So N is the number of moles of electrons that are transferred. So using this equation, we can calculate cell potential under non-standard conditions when we know the standard cell potential. And the standard cell potential we can look up in a table for any given cell or for any given half reaction, and then we can calculate it for the cell. Now there are other forms of this equation that you will see sometimes, but they all accomplish the same thing. We can use this to convert between standard cell potential and cell potentials under non-standard conditions. So let's take a look at an example where we would use this equation. So we want to look at a galvanic cell that uses the reaction copper plus iron 3 positive gives us copper 2 positive plus 2 iron 2 positive. What is the potential of a cell at 25 degrees Celsius that has the following ion concentrations? And we're given the concentrations of iron, copper, and iron 2 positive. So in order to use the Nernst equation, we need to know the overall cell potential. So we have, in one case, copper going to copper 2 positive, and then we also have iron 3 positive going to iron 2 positive. So copper goes from neutral to 2 positive. So copper lost electrons, which means it's the one that gets oxidized. So it undergoes oxidation. Iron goes from 3 positive to 2 positive, so it gained an electron, which means that it undergoes reduction. So we can write out the reactions for this. Solid copper forms copper 2 positive, and it loses 2 electrons in the process. And 2 Fe3 positive. Fe3 positive gains an electron, but there are 2 irons, so we need 2 electrons. And that gives us 2 iron 2 positive. So if we go back to our table of standard reduction potentials, we have copper, which has a potential of 0.34, but is being oxidized, so we're going to reverse that. And then we have iron 3 positive up here, going to form iron 2 positive, which has a cell potential of positive 0.77. So if we go back to our question here, so we found that copper has a cell potential of 0.34 volts, but since it's being oxidized, that's negative 0.34. And iron has a cell potential of 0.77 volts. So if we add these together, negative 0.34 plus 0.77 gives us a cell potential of 0.43 volts. So I'm going to go on to another slide here so that I can have some space to work this out. So we have the Nernst equation, which tells us that the cell potential is equal to the standard cell potential plus, oops, that's minus, not plus, minus 0.0592 volts over N times the log of Q. So we need to calculate what Q is. So if we write Q for our reaction, remember we only write what is aqueous, so we would have copper 2 positive times iron 2 positive squared over iron 3 positive squared. And these two are both squared. So if we plug in our concentrations, copper had a concentration of 0.25, and iron 3 positive had a concentration of 1 times 10 to the negative 4th. So if we take 0.25 times 0.20 squared over 1 times 10 to the negative 4 squared, we get 1 times 10 to the 6th. So we can now plug in all of our variables. The cell potential is 0.43 volts, standard cell potential is, minus 0.0592 volts over the number of moles of electrons being transferred is 2 times the log of 1 times 10 to the 6th So if you put that into your calculator, 0.43 minus 0.0592 divided by 2 times the log of 1 times 10 to the 6th, we come up with a cell potential of 0.25 volts. Now we can also calculate the cell potential, or the standard cell potential, at equilibrium. So we have delta G naught is equal to negative NFE naught, and we also know that delta G naught is equal to negative RT ln of K. So we can set those two equal to each other and do some mathematical rearrangement here. And we come up with that the cell potential, the standard cell potential, is equal to 2.303 RT over NF times the log of K. Or if we want to get rid of this whole factor here, we just establish that that reduces to 0.0592. So the standard cell potential is equal to 0.0592 volts over N times the log of K. So if you had the equilibrium constant and wanted to calculate the standard cell potential, you could do that. Or if you had the standard cell potential and needed the equilibrium constant, this is the equation that you would use. So we can actually plot the standard cell potential versus the equilibrium constant. So when the equilibrium constant is greater than 1, the standard cell potential is greater than 1. And you can see in most cases, K is much greater than 1. And the larger K gets, E cell gets up to between 1 and 3. If K is less than 1, then the standard cell potential is also less than 1. So there are 3 different ways we can actually use to determine an equilibrium constant. We can determine an equilibrium constant based on concentration data. We can determine an equilibrium constant from thermochemical data. So if we know delta G naught, we can plug that in and determine, we already know R and T, so we can use that to calculate our equilibrium constant. Or if we have electrochemical data, we can take the number of moles times the Faraday constant times the standard cell potential over RT and also calculate K. So we can calculate K whether we have concentration data, thermochemical data, or electrochemical data. So comparing E and delta G, and we can use that to look at whether a reaction would be spontaneous and what type of cell that is. So if we have a galvanic cell potentials for a galvanic cell under spontaneous conditions are usually positive. We know that delta G has to be negative for a spontaneous reaction. So if you plug that in, you're going to get a positive cell potential. If you have a situation where delta G is positive, that's a non-spontaneous reaction. For a non-spontaneous reaction, E, the cell potential, would be negative. So that's the case where you have an electrolytical cell. We're forcing this reaction to happen. We have to give it some energy in order to cause this reaction to happen. So that's going to be non-spontaneous. So an electrolytical cell uses electrical energy to convert to chemical energy. If you're at equilibrium, where delta G is 0 and E is 0, then you have a dead battery, which means no current is flowing. So to look at an example of an electrolytical cell, so if we have something like chlorine acting as our anode, which is where oxidation occurs, and sodium acting as our cathode, which is where reduction occurs, this reaction does not happen spontaneously. You actually have to have a battery here, which pulls electrons from your anode and pushes them into the cathode. So the battery here has to do some work to cause this reaction to happen. This is not spontaneous by itself. So we're actually going to stop here, and this wraps up our electrochemistry.